Greetings, AP Chemistry students. It's Saturday morning, about 11 o'clock. You all will see this on Monday, which is kind of weird. But anyway, so we're going to talk about the assignment that I gave you last Friday on limiting reactions. Make sure everybody's cool with that. And then we're going to introduce the lab, and then I will turn you all loose. So let's talk about that assignment from yesterday. So on the honky tonk, 2 steps. So in this space here, okay, Eli, Evan, watch. You want to make sure that you show me what you're canceling out, okay? Just do not let magic happen. So what you should see is that it's 0 order with respect to one of them and 1st order with respect to the other one. Now, so here's the classic thing. So you've got this overall reaction 2A plus B yielding C plus D. So if this was an elementary reaction, in other words, it happened in one step, if this was the actual mechanism, your rate law, because there's a coefficient of 2 in front of this, would be K times A squared times the concentration of B. So if, this is a huge if this was a one-step reaction, and this is the only thing that was involved, it would be the concentration of A squared, concentration of B, boom, it would be a 3rd order reaction overall. You double the concentration of A, you're going to quadruple the reaction rate. If you double the concentration of B, you're going to double the rate. If this was just if this was done in one step. Now, I'm not saying that isn't the overall reaction, but if it was, this is what would happen. But what we're going to do is see, hey, does this really match out? So what you should see is that even though there's a 2 in front of that A, it's actually 0 order with respect to A. So no matter what you do to the concentration of A, it's not going to affect the rate. I'm not saying A doesn't have to be there. It does. It's just not going to change the rate. So differentiate between those 2 concepts. So your value of K, if you leave it in minutes, which is cool, okay, it should be like 0.0 something. If you're hardcore and you want this in terms of seconds, it's going to be something times 10 to the negative 4th. Now, when you get to question 3, what we're looking at there is that there's 2 different ways we could potentially explain this reaction, okay? So notice that you have slow steps and you have fast steps. Remember, reaction cannot go faster than the slowest step, okay? So your intermediates, on that first one, on number 3, you're going to have 1 intermediate, which is E, and then on the second one, you're going to have 2, which is going to be E and F. So remember, your intermediates is like if I throw this thing up in the air, and it goes into that transition stage where it's somewhere not quite blue, not quite purple. It's kind of like this. So they're there, they get used up, they exist, but then you use them up in the next step. Sometimes if it's a really, really fast reaction, we can propose that they're there, but we would never actually be able to see it because as soon as it got produced, boom, it would get used up again. So what you want to do is look at this. So on that first one where you have the slow step is A plus B yielding C plus E, and that's your slow step. So if this was the actual mechanism, then that would be dependent upon both concentrations of A and B, okay? Because those would be it. Now, on the second mechanism, your slow step is just B turning into C plus E. This one is only dependent upon the concentration of B. And that's what matches what we observe. So in both situations, you're going to end up with the same overall reaction. But the second mechanism allows us to match up with what we observe in terms of the actual rate law. Okay. On number 4, that's the only really one that's mathematical. You should get, if you're in hours, should be around 40 hours. If you're hardcore and you want to go into seconds, it's about 10 to the 5th. On that second page, all of those are just rates. Remember, if it's an elementary reaction, it just happens in one step. So if, like for example, you have the O3 plus nitrogen monoxide turning into oxygen and nitrogen dioxide, okay? So since if this was an elementary step, it would be dependent upon those. There's no coefficients. So this would just be R, some constant, times the concentration of your ozone, times the concentration of NO. There you go. On 7C, where it asks you to list the intermediates, there should be 2 of those, okay? On the book problems, that first one's just definitions, not a big deal. And remember, if it's unimolecular or bimolecular, there's 2 ways you can look at something that's bimolecular. Let's say, for example, you have hydrogen and oxygen turning into water. Okay, that's clearly bimolecular. You can also have bimolecular if you have, like for example, you have hydrogen plus hydrogen combining into making H2. So bimolecular isn't the number or the types of atoms, okay? Bimolecular is the number of particles that have to combine. So this, even though it's hydrogen, this would still can be considered bimolecular because 2 hydrogens would have to combine to produce H2. Unimolecular, the only time it would be unimolecular is, let's say you had the decomposition of hydrogen peroxide into hydrogen and oxygen. This would be an example of something that's unimolecular. Anyway, the rest of those should be pretty straightforward. On 72, just to kind of make sure everybody's cool with that, the answer to 72 is that iodate with a charge of 1 minus, which is that intermediate. So you're going to show that canceling out, and then you're going to end up with your rate law. Okay, so that should be pretty much straightforward. Now, at this point, Ms. Calhoun, if you could hand out this lab to all the kids. It's a rather catchy title. The exceptional analysis that is oh so fine of the reaction rate of iodine. So get that handed out, and then we'll talk about the lab. Okay, this way. So get those handed out. Merle, help her out. Okay, maybe she needs help. I'm sure you all can handle it. Okay. I'm not going to stop this video. It's going to sound horrible, but I'm not going to walk around, turn it off, and then turn it back on. So, so you all will be watching this Monday. So either the K-State Wildcats are dancing, and then the Final Four, or it's a sad day and they're not. So, Ema, you're either really, really happy at this point, or you're kind of sad. One of the two. So we'll figure that out. All right, so let's talk about the lab. So down here at the bottom, okay, here's the reaction that's going to take place. Bottom of page 1, okay? Everybody got this? Focus, okay? Aspen, focus. So you've got acetone, CH3, double bonded with an oxygen, CH3, okay? Plus iodine yields this new structure, CH3, C, double bond oxygen. And I'm going to draw this separately over here. Plus H plus. Carbon. Hydrogen. Okay. So this is going to be your overall reaction. So this big structure here, this is the acetone molecule. So when you see these double bonds, those double lines, that just means that there's a double bond between the carbon and the oxygen. We'll get into hybridization and all that good stuff later on. So this is CH3. Carbon is cool. Carbon has 4 valence electrons, so it's going to want to bond and with 4 different things. So on the end of this molecule, you have CH3, which is a carbon, a hydrogen, hydrogen. Okay? And this is very symmetrical, all right? And then you're going to react that with iodine. So if, and this is a huge if this was an elementary reaction, this is why we learned that before we did this lab. If this was an elementary reaction, the rate would only be dependent upon the concentration of your acetone and the concentration of your iodine. So if this reaction took place in just one step, acetone reacts with iodine, boom, we're off to the races. It would be first order with respect to each, boom, we're done. They wouldn't have to worry about anything. So the whole point of the lab is like, oh, is that really true? So what you're going to do, and this is this whole process, over here on this experimental procedure, because you've got a lot of words, read through all that, it's basically telling you to go through the process of isolating constants. So you're going to measure out 3 things. You're going to have 4 molar acetone, and this is going to be important. These are the initial concentrations. You're going to have 4 molar acetone, 0.005 molar iodine, and 1 molar hydrochloric acid. So because we're going to be dealing with 1 molar hydrochloric acid, fairly concentrated, you all make sure that you are wearing your goggles at all times, okay? No exceptions. You wear those goggles if you're messing around with this hydrochloric acid. I don't want to come back and go, oh, what happened to Skippy? Oh, he didn't have his glasses on. Skippy, so help me. Don't know. Wear those glasses. And Eli, don't spill anything, okay? Don't spill anything. Catherine, make sure Eli doesn't spill anything. Okay, so what you're going to do is that you're going to get about 50 milliliters of the acetone, the hydrochloric acid, and the iodine, okay? Put them in 3 separate beakers. The iodine will be fairly evident. That has a distinctive color to it. Acetone, the iodine, you might want to label those so that you know which one is which. Now, what we're going to do is we're going to see if the rate changes things. So down here, okay, over here on page 4, okay, so flip over to page 4. And you've got this data table, and you've got mixture, and then acetone, I2, H+, and then a column that says rate, okay? So what you're going to do is that you're going to mix together up here at the top of page 4. It's going to tell you what you're going to mix together. 10 milliliters of your acetone, 10 milliliters of your I2, 10 milliliters of HCl, and 20 milliliters of water. These, even though I didn't put decimal places on the end of them, trust me, these values, these volumes that you measure out, need to be exact, because if your concentrations are off, all these calculations are going to be a train wreck. So even though I say 10, that's 10.0, 10.0, 20.0. So if you'll notice and you do the math, you take 10 plus 10 plus 10 plus 20, 50 milliliters. So you're going to have a total of 50 milliliters, and that's going to be important. Your total volume is going to be 50 milliliters. So down here, what we need here in the bottom chart on page 4 is the concentrations of these values after they are mixed together. Not the initial concentrations. Concentrations after they are mixed together. So what you want to do, and let me kind of show you where I get this 0.80 for that acetone. So this is going to be mixture number 1. So what we're going to use is M1V1 equaling M2V2. Okay? This isn't molarity, MAVA equals MVV. This isn't acids and bases. This is dilutions. So what you did is that you measured out 10 milliliters of a 4 molar solution of acetone. So you went to the stock solution and you got 4 4 molar solution, and you got 10 milliliters of it. So what we want to know is what's the new molarity going to be once the total volume becomes 50 milliliters, okay? So this is where this comes from. If you don't believe me, okay, take your calculator, all right? Take your calculator. Peyton, you can do, somebody, this is what you're going to do. So you're going to take 4 times 10, and you're going to get 40, check my math, and then you're going to divide that by the total volume of 50, and if you divide that by 50, you're going to get 0.8. So that 0.80 is the concentration of the acetone after it's been mixed. So what you need to do is you're going to do that for all of these, the iodine and the hydronium ions. The reason I would choose hydrochloric acid is because it's a strong acid. We're assuming that it's fully ionized. So what you should have, I'm going to fill this in just to make sure everybody's cool with what you should get. So when you get done with this first line, your iodine should be 0.0010, and your hydronium ion concentration should be 0.2. So I'm going to put this up there so you can verify that when you do this, you got these right. Because if these concentrations are wrong, everything's going to be a train wreck going forward. So when you get done with that first one, you're going to use M1V1 equals M2V2. This is going to be your initial set of concentrations after they've been mixed, okay? Now, that's what you need to do. You need to get all that together. So here's what you're going to do. And listen to me very, 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 very carefully, because the sequence is so important to this. So what you're going to do is you're going to take a beaker, and you're going to mix together the water, the acetone, and the hydrochloric acid. So you're going to mix all that together, okay? Do not add the iodine at this point, okay? Don't add. You're going to get all that mixed together. Then what you're going to do is that you're going to have ready a couple of clean test tubes, okay? So this is going to be important. You're going to have a couple of clean test tubes. So you have this ready to go. You're going to have your 10 milliliters of iodine ready to go, okay? And then you're going to have your phones, because you need your phones as stopwatches. So iodine, in case you haven't noticed, has a really distinctive color. So what you're going to do is you can take that iodine, and as soon as you add the iodine, boom, you're going to start the stopwatch. Add the iodine, start the stopwatch. Then what you're going to do is you're going to take that solution, and you're going to pour that into, you won't pour all of it because there's more than what you need, but you're going to pour that into these 2 test tubes. Now, so here's what's going to happen. So let's say Violet and I are partners, okay? Violet, you and I. Focus, okay? So what's going to happen is that I'm going to give Violet one of these, and I'm going to take the other one, okay? And she's going to have her timing device, I'm going to have my timing device. We're going to work completely independently. So what's going to happen is that she's going to have hers, I'm going to have mine. So what's going to happen is that this iodine is going to get consumed. So if you go back up here to this reaction, basically what's going to happen is this. This iodine is going to get split up into 2 different iodine atoms. This is going to be like an intermediate state. And then what's going to happen is that it's going to come in here, and it's going to kick out one of these hydrogens, and it's going to take its place over here, where now you're going to have an iodine in the place of this. So this, if you hearken back to the days when we were working with permanganate, okay, permanganate had a distinctive color, and you would add permanganate until it took on the color of that magenta of that permanganate. Basically, we're going to do the opposite of this. You're going to start with iodine, and as that iodine is going to get consumed, this solution is going to become more clear. So what you need to do, listen to me very carefully, what you're going to do is that you're going to mix it all together inside the beaker, okay? So here's this beaker. You're going to have everything mixed up. Boom, add the iodine. Add the iodine, hit start on your stopwatch. Boom, you're timing this thing. Violet is going to have hers. I'm going to have mine. I don't want to know what Violet's doing. Violet's not going to know what I'm doing. So what you want to do is and there's different techniques. What it's going to tell you in the lab, and this works well, is that you want to look down through this test tube. So you're going to look down. So here's the test tube. And you're going to, there's your eyeball, okay? And you're going to look down, and when that's the reason that you want to use white paper. So as soon as that solution goes clear, you're going to stop your stopwatch. Because at that point, we're going to assume that the iodine has all been used up and the concentration has gone to 0 at that point. So the reason that I don't want to know what Violet's doing, and she doesn't want to do what I'm doing, is we want to do this independently. So what you're going to do is you're going to take the average of the two times. When I did it, I got about 180 seconds. That's an ish. This is very, very temperature dependent, hugely temperature dependent. So what you want to do is you're going to record the temperatures. I'm going to have the old school thermometers over there, okay, the old school, the OGs, okay, the OGTs, the original gangster thermometers. Measure the temperature of that beaker. Okay, it's probably going to be around 20 degrees, 22 degrees Celsius, something like that. You're going to need that number later on. So what you are ultimately after is the rate. And we're going to base the rate on the change in the concentration of the iodine. So to get this over here on page 4, this rate column, that's going to be the change in the concentration of iodine per unit of time. Now, so the initial concentration of the iodine is 0.001. Okay, again, that's the concentration of the iodine after it was mixed together. So you're going to take 0.0010, because that's the concentration of the iodine, okay? And that's your initial concentration. Your final concentration is going to be 0, so technically this is going to be a negative number. And then this is molarity. This is molarity. Not moles, molarity. And then you're going to divide that by that time, okay? Now, when I did this, and this is just for reference, okay? When I did this, and again, this is very temperature dependent, it's very concentration dependent. When I did my data, when I did this first trial, I got 6 times 10 to the negative 6 molarity per second as my rate. Yours could be vastly different. Not vastly, if you get like 6 times 10 to the negative 8th, something has gone wrong. If you get 6 times 10 to the negative 2nd, you have done something horribly wrong. This is a ballpark. It's going to be something around that value, okay? So, Violet's, you're going to do hers, I'm going to do mine. We're going to stop them when those test tubes go clear, okay? There you go. You're going to use the change in the concentration to get of the concentration of the iodine to get the rate. That's the only thing that we can measure. Now, what you're going to do, then you're going to go down to the next one. So on the next one, you're going to have 20 milliliters of acetone, 10 milliliters of iodine, 10 milliliters of hydrochloric acid, 10 milliliters of water. Notice that what we're keeping constant on all of these trials is a constant volume of 50 milliliters. So no matter what, you're always going to add up to 50. And again, rinse out that beaker, start over from scratch. Here you go. You're going to measure these things out. It's what I would recommend, especially on that iodine, okay, maybe keep like a separate graduated cylinder just for your iodine concentration. If you really want to get bougie, that's kind of a Morella term, even though she's not part of the lab, we'll turn Morella bougie, okay? There's graduated pipettes over here on where Aspen works, okay, over here on this side of the lab, imagine that. There's a rack and it has like 10 milliliter volumetric pipettes. If you really want to get bougie, said it with a southern accent, you can get those and use that just for those 10 milliliters, okay, measurements. But no, forget that. Don't do that, because then you'd have to wash it out every time. Just use a graduated cylinder. Don't get bougie. Or if you could if you wanted to, but I don't recommend it. Mainly because you got to rinse it out every time, and it's easier to rinse out the graduated cylinders than strike that from the records. Do not touch the pipettes. Do not touch the pipettes. Let them go. Don't get bougie. Forget, strike that from the record. I might edit that out. Probably not, it's not worth the effort. Okay, so what you're going to do is you're going to run 4 trials. I don't want to bias you, but hopefully what you see is the first trial takes the longest time to run. The other ones should go faster, okay? So hopefully your first trial takes longest, the other ones go a little bit slower than that. Now, listen to me, Evan, Eli, listen to me. The heart and soul of this is that you are going to try and figure out the order of exponents, and you're going to have R is going to equal K, concentration of your iodine, concentration of your acetone, concentration of your hydronium ions. Now, this is why we know this isn't an elementary step reaction, because what you'll see is the concentration of the hydrogen actually impacts the rate of this thing. And you wouldn't think it would. It's like, oh, hydrogen is a product. How can that happen? What that tells you is that this is not a simple one-step reaction. There's a wizard behind the curtain pulling some levers that are somehow going to include that hydronium ion. So what you want to do, listen to me very carefully, and I take you through this. So here on page 4 it says, substituting the initial concentrations, write equation 3 as it would apply to reaction mixture 2. So on this line, where it says rate 2, you're going to have R equals K, 1.6 times the concentration of X times 0.0010 times the concentration of Y, and then 0.20 concentration of Z. So this is what I want down here on this line where it says rate 2. This, right here. Do not make this difficult. This is what I want, right there. Okay? Do not make this difficult. Then you can do the same thing with rate 1. Okay? It's going to be the exact same format. The only difference is going to be, hey, we're going to put in the concentrations from that. Now, down here at the bottom of page 4, I'm going to tell you, divide reaction 2 by reaction 1. Okay? At this point, you're going to know the rates. You're going to know this column over here. You're going to know these rates. So then you're going to show the cancellation process. You're going to show things canceling out. This is a process, okay? And hopefully what you see within your rounding error is that it's first that X has a value of 1. It's like first order. So what you should see, and then you're going to do this thing, and you're going to show how you're going to get Y, how you're going to get Z. Hopefully, what you should see, I don't want to bias you, but I'm not going to be here to answer your questions because I'm going to be in D.C. when you all are doing this lab. Hopefully, what you should see is that it's first order with respect to the acetone. It is, first order with respect to acetone, 0 order with respect to iodine, and first order with respect to your hydronium ions. So, in theory, it should go first order, acetone, 0 order iodine, first order acetone, or hydroniums. So 1, 0, 1, second order overall. Hopefully that's what you see. Now, what I want you to get done today, or at least done by the time you come into class tomorrow, is that what you're going to do is you're going to show, and listen to me, and in big bold letters, I tell you, show the calculations in the space below. You're going to find the experimental value of your K, your rate constant, for all for trials. Make sure it has the units on it, okay? Make sure it has the units. Vanessa, listen to me. Focus. You and I, right here. Right here. Make sure every K value has units on them. Okay. And then you take the average of those, okay? So you're going to show all the calculations of K, because at this point you're going to know what the rate law is. It's overall order second. And then you're going to come in here, you're going to show the 4 calculations of K, and then you're going to take the average. When I did my data, based upon when I did this lab, my K value, come on, my K value was 10 to the negative 5th, and not to be a hypocrite, and the units, my units are m to the negative 1, s to the negative 1. So I don't want to bias you, but that's what I got based upon the data that I collected when I did this lab. That's going to be 10 to the negative 5th. So what I want you to have done for tomorrow, hopefully you can get all 4 reactions run, and then you got to work quickly, don't lollygag, okay? Focus on getting the reactions run, and then get through the middle of page 5 through tomorrow, because you have to have this K value before you can do anything else for the lab tomorrow. Okay, we're done. Peace out. I will see you all tomorrow.